of you who are actually listening online live, and those of you who will join us on the recording. I'm happy to do this. I'm Dave Waits. And today I'm going to talk about two topics. I'm not going to actually go in the order that's listed on the syllabus, but in the order that makes the most sense. But I will cover both topics, both confocal microscopy and colloids. I want to give you an introduction to colloids. I'll give you a discussion of confocal microscopy as it's applied to colloids, and then I will give you examples of both the use of confocal microscopy and other types of techniques that you have learned about already in this course as they apply to the study of colloids. But the main goal is to discuss the physics of colloidal particles. So colloidal particles are one example of a dispersed system. That is, a system of particles immersed in a fluid. You're actually fairly familiar with the other examples as well. Colloids are solid particles. If the particles are liquid, then they're emulsion. They're drops of one fluid in a second fluid. And if they're bubbles or gas, then you have a foam. Colloids have the advantage of a much greater stability than either emulsions or foam. Moreover, colloidal particles being solid are not deformable, whereas foams and emulsions can be deformable under certain conditions. Typically, colloidal particles are described as something of order a micron and smaller. I will actually broaden that description and discuss particles that are a few microns as well. But the main point is that Brownian motion is important in understanding the physics of the particles. Actually, colloidal particles are much more ubiquitous, and if you want to generalize it to dispersions, but particularly colloidal particles are very ubiquitous. They're around us in many ways that perhaps you're not completely aware of. They're very important in biology and in biophysics. If you think about it, viruses, macromolecules, organelles, all of these behave very much like colloidal particles. Brownian motion is very important. They're more or less solid, at least the way they behave in biological systems, and they act very much like colloidal particles. Colloidal particles are very important for probes, for a variety of different assays in biology. Quantum dots are used to label things, spores, bacteria. They all act like colloidal particles. More generally, colloidal particles are very widely used in processing of many types of materials. When you paint, you're using colloidal particles. In fact, most coatings involve some kind of colloidal particles. Ceramics also at the early stage involve colloidal particles. The ceramic particles in a fluid, the early stages when you make the green bodies, those are again colloidal particles. Now, the real reason that you use colloidal particles is, in a sense, to control the rheology, to control the flow properties. Basically, you're making, by splitting a solid into very, very small particles, you have the solid, you have the characteristics of the solid, but the flow properties are controlled by the continuous fluid, by the fluid phase itself. And you can pack up to volume fractions, say, of 50%. Half the volume can be filled with the colloidal particles, that is, filled with a solid. Nevertheless, the system will actually flow as if it's a liquid, because the other half, the liquid half, really is what sets the control of the flow. And so it's the control of the rheology that gives colloidal particles their most important use technologically. So they behave like a solid, a continuous fluid. This also allows you to process the solid particles. For example, when you coat something, when you spread the particles, you spread them like a fluid, but once the fluid disappears, that's the way paint works, the fluid disappears, and the colloidal particles then fuse together to make a solid coating. Okay, the properties of the colloidal particles are set by the particle density. By that, what I mean is not the actual density of the particle. That plays an important role. What the density of the material is in describing the properties, it's really the buoyant density. But what I really mean by particle density is the number concentration, the number of particles per unit volume. And you can understand the nature of colloidal particles. In fact, you can understand very, very generically all of soft matter physics by just understanding this one fact. Typically, a solid has in a cubic meter something like, I don't know, 10 to the 27 atoms, a large number. I calculate that by saying there's one atom per cubic nanometer. That gives you 10 to the 27 atoms per cubic meter. By contrast, if a colloid is a micron in diameter, then you have something like 10 to the 18 particles per cubic meter. It's a very, very large reduction in the number of particles or the density, the concentration of particles. So this has many important consequences. For example, latent heat of phase transitions is just too small to measure. It's never something that you can actually measure, whereas you can certainly measure that in a normal solid. The pressure, the osmotic pressure, which is just given by the number density times kT, is much, much lower for colloidal particles than for ions or anything else in a fluid. So the osmotic pressure from the colloids themselves typically is very low. And again, if you calculate that for typical examples that I've given here for 1 micron, it's about 10 to the minus 3 pascals, millipascals. This also sets the value of the elastic constant. The pressure has the same units of the elastic constant, and the elasticity is just given by these same units. If it's thermal, if thermal energy plays a role, it's just kT divided by the volume of a particle. And that is, in fact, the essence of the difference between soft materials and hard materials. Soft materials have elasticities of order pascals or fractions of a pascal, as we just calculated, whereas hard materials have elasticities that are much, much larger, basically not because of the interaction energy. The elasticity is just given by the interaction energy divided by the volume of the interacting particles. So the elasticity of a normal hard material is given by the energy of the bond between the atoms in the material, which might be, if it's a covalent covalent bond, it might be electron volts, and divided by the volume occupied by a typical the density of the bonds, and that might be some number of angstroms. And that gives you values that are of the order of gigapascals. By contrast, a colloidal system, the energy is more typically thermal energy. It can't be anything less than thermal energy or it wouldn't stay together. So it's typically thermal energy, and the density is typically cubic microns. And that gives you something of order pascals or some fraction of a pascal. And this difference, this 9 to 12 order of magnitude difference, arises only, and I repeat, only because of the density. The difference in the energies is maybe at most a factor of 100. The 10, 12 order of magnitude difference that you might have between the elastic constants arises because of the difference in the scales. And for colloidal particles, then it's very easy to understand the origin of this difference of the scales, because the physics of the interactions of the system itself arise from the interactions between interactions due to the colloidal particles themselves, and they're much larger, and hence they are a much softer system. Now, colloidal particles are studied by a large number of techniques. Traditionally, the colloidal physics was studied by light scattering techniques. The particles are of the order of a fraction of a micron to a micron in diameter. Their separation is of the same scale, and that corresponds nicely to the wavelength of light. You also can study them as they get smaller using either X-ray or neutron scattering, and those have both been commonly used. So you typically use static light scattering to study the structure, dynamic light scattering to study the dynamics. People have invented or have used very small angle, both static and dynamic light scattering. That's very, very similar to very small angle neutron scattering. One thing that's been used with light that hasn't been used with neutrons or X-rays yet is diffusing wave spectroscopy. That is to take advantage of the very large scattering of the particles. Typically, they scatter very strongly, and then you can assume that the light itself diffuses through the sample, and you can reinterpret dynamic light scattering under those conditions. That's something that I won't have time to discuss, but it's commonly used for the study of colloidal particles. Now, more recently, light scattering and scattering techniques have been replaced by microscopy, and that's why confocal microscopy and colloids are the two lectures that I'm going to discuss, because confocal microscopy is now a tool that is very widely and successfully used to study the behavior of colloidal particles. Finally, as I mentioned, because the main purpose, the main use, the technological use of colloidal particles is to control the rheology, then rheological measurements are also very commonly used and are very important to understanding the properties of the system. And I will describe some of that in these lectures. Now, one development that combines light scattering and microscopy with rheology is microrheology. That's the use of probe particles and the motion of probe particles to actually interpret the rheology. And again, that's a somewhat more advanced topic that I won't get to in these lectures. So let's turn to confocal microscopy for a minute. You can understand that in a fairly simple way. It's a microscope, but rather than imaging the sample directly, what happens is that, as shown in this diagram, and let me see if I can point some things out here. Yeah. Here, you use a laser that runs through the optical axis of the microscope and through the lenses of the microscope, but instead of forming a broad image at the focal plane of the sample, it is focused to a diffraction limited spot at the sample point. At that point, it excites fluorescence, and the fluorescence is passed through the same optical chain and back up to a detector. However, there is a pinhole that exactly matches the diffraction limited spot that is confocal to the focal plane of the sample. That is, that an image of the collected light is made exactly through this pinhole. What that means is only light that emanates from the diffraction limited spot on the sample can actually pass through the pinhole. If the light emanates from any other point on the sample, it is not focused at the pinhole and it doesn't pass through the sample. If it's up or down, left or right, then it's imaged to one side of the pinhole. If it's in front or back, then it comes to a focus at some different point, and very little of it actually passes through the pinhole. So the role of this confocal pinhole is to block all the light except for that emanates from the diffraction limited illuminating spot of the sample. So this is a way of imaging the light that comes from just one point in the sample, one three-dimensional diffraction limited spot within the sample. Then using the power of computers and scanning apparatus, this point is scanned in 3 dimensions. First it's scanned in a plane, and then it's scanned into a 3rd dimension to make up images of the whole sample. So confocal microscopy is always done through a scanning technique. The best imaging is done by scanning a point source, although you can also scan a line as well and focus that through not a pinhole but a slit. The resolution in that case is not quite as good, but it's still quite superior to normal microscopy. Here's a picture of one confocal microscope that exists in my laboratory. There's this big pink box because the sample itself is kept at constant temperature. The actual confocal portion of this microscope is this unit at the top. This is a what's called a spinning disc. It's a slightly more complicated version, but it's essentially the same thing. Rather than rastering the pinhole and the focal plane, a focal point in 2 dimensions, there's a disc with many focal points with an array of microlenses, and that's spun very rapidly, and the discs then cover the whole region of the sample. But the essential physics of this is exactly the same. Now here's a typical imaging and how one goes about doing the actual imaging. You can see what this is. The image on the right is a reconstructed image of a colloidal sample. In this case, all the particles are the same, so we've rendered them with a drawing program to have the same size. But this image is made up by taking a series of slices or 2-dimensional scans. In this case, it's a point scanning microscope. So each of the scans is made up of a scan in 2 dimensions, and then the slices are put together and reconstructed into a 3-dimensional image. Something like this might take, if you have one of the modern confocal microscopes with very fast scanning, the scanning can be at least at video rates, if not faster, in a plane, and you can scan a full 3-dimensional image in something like a second or a fraction of a second, depending on how many slices you actually collect. More typically, it's a little bit slower, but nevertheless, you can collect data in 3 dimensions with up to 1 or 2 frames per second. Oftentimes now in 2 dimensions, if you're just taking a single slice, you can go at least at video rates, often much faster. The other technique that I will discuss briefly and I will use is rheology. Rheology with soft materials, in all cases with soft materials, one is interested in the elasticity of the material, but all materials have both elastic contributions and viscous contributions. They're viscoelastic, and the way to tease out the difference between the elasticity and viscosity is to recognize that they depend differently on strain. So elasticity depends on the total amount of strain, whereas viscosity depends on the strain rate. So if you have something that depends on both the strain and the strain rate, or the derivative strain with respect to time, the way you tease these out is you apply an oscillatory strain. You look at the in-phase component of that, the component of the response of the strain that is in phase with the drive is that due to the elastic contribution. The component that is out of phase, that lags, that is due to the viscous or the loss component, and it just reflects that it's due to the derivative. If you use an oscillatory motion, then the derivative is just a phase shifted by 90 degrees. And so you can sort out by measuring both the in-phase and out-of-phase components, you can sort out what we call the elastic modulus, or we label it as G prime, and the viscous modulus we label as G double prime, because often we will write this as a complex number, as a complex quantity, just for ease of manipulation. The next slide here shows again how this is written, and the stress is now given on this equation on the right. Let me take my pointer here. This equation here, the stress is given by the sum, the complex sum of the real part, the elastic component, and the viscous component, and this is written as a complex number times the strain. And this term, the fact that there's this I here, means it's essentially proportional to the strain rate. This is a typical result. I will come back to this later, but here I'm showing the elastic component. I've stitched together data by scaling data. I'll describe how one can do this, but I've stitched it together to get many orders of magnitude and frequency. Typically, you can only measure 3 or 4 orders of magnitude if you use a rheometer, because you're limited to the frequencies at which you can drive the rheometer. But you can imagine the actual rheology of a system extending over many orders of magnitude of frequency. And I'm showing this because this type of behavior is what one often sees in studying the rheology of soft systems. Almost all soft systems will have something that is reminiscent of this behavior. In the central region of this frequency range here, it's the lower frequency range, you see the fact that the elastic modulus G prime dominates, and the system is actually elastic in this region. There is a viscosity. There's a viscous component. It's much weaker. It's about an order of magnitude less, or half an order of magnitude less in this case. It, in this region, is also essentially independent of frequency. And that's a bit of a puzzle still, why it's independent of frequency. There's a variety of reasons, and there's one simple reason which I'll tell you in a second. At high frequencies, you see there's a crossover, and eventually the loss modulus dominates, and that's this part here. The loss modulus dominates, and it's larger than the storage modulus, which implies that at high frequencies, the fluid-like behavior of the material dominates. And you can understand this in a very simple way. Since there is both a solid-like component and a fluid-like component, and you're oscillating your stress or your strain on that, eventually the contribution of the stress due to the fluid, which is increasing, the stress increases as a function of frequency. The stress always depends on the strain rate. So as the frequency goes up, the stress goes up. Eventually, the contribution of the stress due to the loss component, due to the fluid-like component, dominates everything, and the system just exhibits the behavior of the viscous properties of the underlying fluid. And that's shown here at these high frequencies. And that's almost always the case if the material has some fluid-like component. On the other hand, if you go to the very low frequencies, you can see what's happening here. These data are not so clear, but you can see that the storage modulus, the elastic component, slowly decreasing. And if anything, there's some indication that the loss component, the viscous component, is starting to increase again. In fact, what's happening is that if you go to very, very low frequencies, and here these are much lower frequencies than you can access with these experiments, the sample again will begin to flow. And this happens with many types of soft materials that ultimately will relax. They are solid-like over very long times, but eventually they relax and become fluid-like. And if they relax and become fluid-like, then at the very lowest frequencies, the loss modulus, the viscous component, has to begin to dominate, and this has to go through a peak, and the storage modulus needs to drop. And it's this the fact that the loss modulus is going through a peak at low frequencies and increasing at high frequencies. So there's some valley, and that's essentially why you get this more or less constant region of frequency dependence in the intermediate range. And I see there's a question from the Colorado School of Mines. What kind of rheometer is used in this study? This particular study was done with a controlled strain rheometer, an old controlled strain rheometer from rheometrics. It can also be done with a controlled stress rheometer. It's a commercial instrument that controls either the strain or the stress, applies, in this case, an oscillatory strain or an oscillatory stress, and measures the opposite component. Okay. So let's go back now. I'm going to come back to the what are the units on horizontal? Questions. What are the units on the horizontal? That's this. It's frequency, but there's a scaling factor. You can imagine that this is a frequency dependence. It's not. No, it's frequency, so it's per second, radians per second, not meters per second. But there's a scaling factor, and let's not pay too much attention to this at this point, because I'm going to present these data in much more detail, and you'll see exactly how I get them. I just wanted to have something here that would show the full range of behaviors possible. Okay, let's go back to colloidal particles. Unfortunately, the movies that I have don't play. This would be a nice movie. This is an image, a video of colloidal particles. Each of these white dots is a colloidal particle. Hopefully in the online version we'll actually get the movies to play properly. These particles are undergoing diffusive motion, and these are imaged with a confocal microscope that's rapidly collecting data in one plane. And so you can watch the particles diffuse. They will stay within the plane for some period of time. For example, this particle is in focus, as this one is. This is somewhat out of focus, so they'll stay in the plane that's focused for some period of time, and then they'll move up or down, and go out of focus. So here, these are particles that are above or below the plane that are not imaged quite as well because they're not in the plane of view. So the important thing about this for the colloidal particles is that they are always thermalized. That is, they can explore all of volume, but they do that because they're in thermal equilibrium with the fluid. They undergo Brownian motion, they explore all of phase space, that's volume space, and they do that through the equilibration with the fluid. The fact that they're thermalized lets me think about them in certain ways, and very often what I'm going to do is I'm going to ignore completely the behavior of the fluid. Let me give you a specific example of what this thermalization looks like. On this slide, I'm showing, again, these particles are, these images are actually movies taken with a confocal microscope of a pair of particles, each undergoing independent diffusive motion. And what you can do with a confocal microscope, and this is basically how one goes about analyzing the data like this, is each image, you identify all the particles, and you identify exactly the location of the particle. Now, normally if you worry about a microscopy, you think of the resolution of a microscope as being given by the Rayleigh criterion, which is it's half of the wavelength of light, or some fraction of the wavelength of light. And while that is correct, what that really refers to is how close can two particles or can two points in the image be so that you can resolve the fact that you have 2 points. Because what you're really doing with the Rayleigh criterion is trying to resolve the difference or the spatial separation between two diffraction images. If you only have a single particle, which is the case, for example, in these two images, if you have only a single particle, then you don't have to, you're sure that you only have one particle. You don't have to resolve it from another particle. You only have to find the center of that particle. And since it's a sphere, you know what its diffraction image is. You know what the diffraction pattern of the sphere is. And to identify the location of that can be done much, much more precisely than the Rayleigh criterion, the lambda over 2, would suggest that you can do. You can actually identify the location of a particle using a confocal microscope easily to, say, 20 nanometers. It's set only, or it's limited only by the signal to noise. In fact, if you have a better signal, you can find it even more precisely. This only works, of course, if you have particles that are well separated, that you can identify the centers. You can't do this if you have to deconvolve a group of particles and you don't know where the centers, you don't even know how particles you're looking at. However, for all systems that we typically look at with colloids, the particles are spherical, and it's very easy to identify the center, and then you can locate the position of the particle very easily to, say, 10 or 20 nanometers. So the plot over here on the left is an image that just each frame is represented by a dot. That's the location of the particle measured to within 20 nanometers, and the colors represent the evolution in time. And in this XY plot, we're plotting the Y position measured as a function of time. And you can see these would be microns, but you can easily get resolutions to, say 10 nanometers or that sort of uncertainty. And you can watch the motion of the particle, and this is really diffusive motion measured in real time for a particle in a relatively dilute suspension. To analyze that, as always with the diffusive motion, the best way of analyzing it is to measure the mean squared displacement. That is, you measure what the average displacement as a function of lag time is. You look at all the different lag times of, for example, 0.1 second, and you measure the average mean squared. You measure the average squared displacement, and you plot that as a function of lag time. That's shown here, and you see it's plotted on a log-log plot, and it has a slope of 1. That's exactly what you expect for a diffusing particle. Diffusion in one dimension is the mean squared displacement is 2 times the diffusion coefficient times time. That's just the Einstein prediction. It's just the type of motion that you see in diffusion. However, in this case, you have all the data that you've collected to actually determine this diffusive motion, and so you can do much more with this. First of all, of course, you can calculate the diffusion coefficient. It's just given by the Stokes-Einstein equation. You know K, the Boltzmann constant, you know temperature. You can either measure the size of the particle, A, or the viscosity. You need to know one to measure the other, or you need to know both to measure the diffusion coefficient. The diffusion coefficient is actually given by the intercept of these data, and from this, if you know, for example, the size of the particle, you can measure the viscosity of the system. You can go farther. You can take advantage of all the data. You have all the different data that you've collected. So, for example, you can plot the distribution function, the Van Hove distribution function, or the step size distribution function. If you look at some particular lag time, these data are shown for a lag time of half a second, and you plot the distribution of step sizes. This is just in 2 dimension or in 1 dimension, so it's just going a positive and negative. And you see that you get a Gaussian distribution. You have to get a Gaussian distribution when you have a diffusive motion. Okay, so you can measure that very nicely. Colloidal particles in general, there's an enormous amount of physics that you can do with them. One of the most interesting things from a statistical perspective is to recognize that colloidal particles are essentially like very large, slow atoms. That is, They're thermalized with the background, just as atoms in a normal solid are thermalized with the rest of the solid. In the case of colloidal particles, they're thermalized because of the presence of the fluid, whereas in the solid, they're thermalized with the background of all the other ions or atoms in the solid. But in this case, the particles are very big, so you can actually image them. You can see them with a microscope, and they're relatively slow. You can, by slow, you can calculate a characteristic time. This is a characteristic time, for example, for them to diffuse their own size. And for colloidal particles, that time might be milliseconds or seconds to seconds. That means that you can follow the dynamics. The phase behavior of the colloidal particles are determined just by the way they pack, and I'll show you examples of that. So this is the phase behavior is in many ways, not completely, but in many ways similar to what you get with normal solids. So you can actually use colloidal particles as a beautiful model system to study, in a statistical sense, the behavior of more traditional solids, the advantage being that you can see the individual particles and follow their specific dynamics. One thing that we're ignoring is the fact that there is a continuous fluid, and this doesn't play quite right, but if I started to play, imagine the particle on the left moving just a bit. If it moves a bit, what it does is it pushes the fluid, and these lines are meant to move in. It pushes the fluid, move down, sorry, so that you have this is meant to come down, so you have like a wave of motion of fluid. This is the pressure wave, if you will, due to the pushing of the fluid, due to the fact that this particle has moved to the right. This has an effect, because it's pushing the fluid then will push on the neighboring particle. So what that means is this particle, the one on the left, can interact with the one on the right and cause the one on the right to move due to the presence of the fluid. These are called hydrodynamic interactions. Notice, however, that occurs only when the particle moves, because it has to create this pressure wave. So hydrodynamic interactions, while they're very important, they're also very difficult to fully describe. They depend intrinsically on the motion of the particles. So if you look at a static property of a system, that is, you look at something that's time averaged, then it cannot depend on hydrodynamic interactions. Hydrodynamic interactions can only affect the dynamics of the system, not of the statics of the system. Okay, so most of what I'm going to talk about, then I'm going to assume that the system is thermalized. I'm going to ignore hydrodynamic interactions except as they affect the dynamics, and I'm going to assume that they have no effect on the. So to understand the behavior of colloidal particles, we should really understand something about the interactions between them, and there's a variety of different types of interactions. The most important one is hard sphere interactions. Hard sphere interactions always exist. The best way of understanding hard sphere interactions is simply that no two particles can overlap, can occupy the same place in space. And so if you bring two particles, no effect. Okay, so there's a question here. Last slide, what is meant by no effect of static properties, or what are the static properties? That should be no effect on static properties. So the hydrodynamic interactions are a dynamic interaction, and they don't have an effect on the static properties, on the time average properties. Because they intrinsically depend on the motion of the particles, they can't affect things that time average all the motion out, and so they can't affect static behavior of the time average behavior of the particles. That's what I meant by that. Okay, so back to this slide. Here the interactions are shown in this plot. There is a very strong repulsive interaction. So on these plots, what I mean, I'm plotting the interaction energy as a function of the particle separation. By particle separation R, I mean the center-to-center particle separation, the center-to-center separation between two particles. And two particles can come until they just touch each other, so they're separated by 2 times the radius, or the diameter of the particle, 1 radius for each particle, and then there's an infinite repulsive barrier because they just can't come closer than that. We're assuming that they're non-deformable, and the strength of this interaction reflects the strength of the solid material, which in this case I'm going to assume is essentially infinite. I'm not going to allow for the elasticity of the solid material itself to play a role. That's just, as we described before, that involves the elasticity of a solid, which is between 9 and 12 orders of magnitude larger than the typical elasticities that you will run into with the colloidal particles themselves. So Hydrodynamic interaction refers to the fact that there's an infinite repulsive interaction when they touch, and there's no interaction anywhere else. So this is a sort of idealization. You really can't have something that has such a short-range interaction, but in many cases we can come very close to this. And this is something that's very easy to model with computer simulations, so it's something that's very widely studied. Other kinds of interactions, there's always some kind of attractive interaction. That typically comes, for example, by van der Waals interactions. So any two particles that are made of one material that are dispersed in a material with a different dielectric constant, like a fluid, will have some kind of attraction. It will be a van der Waals or a dispersion interaction. And physically, that comes about from the fact that if you have a fluctuation of the dielectric constant in one particle, that's like a fluctuating dipole, that induces a dipole interaction in the other particle, and you get an induced dipole-dipole interaction. Because it's one dipole inducing a second dipole, and the interaction between the two dipoles, the van der Waals interactions typically fall off as 1 over r to the 6th, so they're fairly short-ranged, but compared to the Hydrodynamic interaction, of course, they're somewhat larger range. This depends on the polarizability of the material, and you absolutely need to have different indices of refraction or dielectric constants than the surrounding fluid. In fact, one way to eliminate the effects of the van der Waals interactions, not completely, but to minimize them, is to make the dielectric constants of the solvent and the fluid to be the same. You can't completely eliminate that because you can make them the same over some range, like for example over the optical range, but that's not to say that they're the same over all frequencies. It can be they're the same over some frequency range, but not all. This is the equation for the van der Waals interaction. I'm not going to go into it in great detail. It's shown schematically. The type of interaction that you have is shown schematically here. It falls off as 1 over r to the 6th. It decays. It really goes from the surface, not from the bulk. And there are many calculations of this kind of interaction for different shapes. It's very strongly dependent on the shape because it's really you have to sum the dipole-induced dipole interaction over all units of each of the solids. It's relatively short-ranged, but it doesn't have to be that short-range, and it's not that short-range compared to the hard-sphere interaction. The calculation of the dipole interaction was one of the great successes in colloid physics, particularly, say, in the middle of the last century. Now, dipole interaction leads to an attractive interaction. The particles can't stick together or can't occupy the same space, so eventually the hard-sphere interaction prevents them from coming any closer. But if you just have a dipole interaction and a hard-sphere interaction, if I go back here, you have this type of interaction shown here, and this is like having an attractive well. They can't penetrate more than this line here, but there's an attractive well here, and if this attractive well is fairly deep compared to kT, then the particles can stick together. If the particles can stick together, then they, as they undergo their Brownian motion, their random diffusive motion, they will eventually come close enough, they'll come close, this close to one another, this distance here, and they'll fall into this attractive well, and if this is much greater than kT, they will begin to stick together, and the particles will no longer remain stable. They won't remain suspended because they'll start sticking together and becoming a big solid block. So you need to have some kind of repulsive interaction to prevent this. One of the most common kinds of repulsive interaction is the charge interaction. That's important in aqueous systems because you can get dissociation of charges in the system. And you can understand that by looking at these two, this diagram of the two walls of, or surfaces, interfaces of two colloidal particles that are approaching one another. Let's say that the intrinsic charge on the colloidal particle is positive. That means that there must be counterions that have been dissociated, and the negative ion is in solution. That's shown here. There's negative ions in solution, and the number of negative ions in this case is exactly equal to the number of positive ions between the two particles. And so this leads to a system where there's a negative charge, a positive charge on the surface here, a second positive charge on the surface here, with negative charges in the middle. And you might think, well, the two positive charges of these two surfaces interact with one another and repel one another, and that's what leads to the stability. And while conceptually that's correct, it's really much better to think that, before I go there, it's really much better to recognize that the effect of these positive charges is to hold the counterions in the middle of the space. They can't really go off to infinity because the electrostatic energy keeps them more or less localized here. The fact that they're localized here means that there's an osmotic pressure due to these counterions. You can't squeeze them together. If you try and bring these two surfaces closer together, yes, you will get repulsive interaction between the positive surface, but at the same time, you will squeeze these particles much closer than they want to be. And that presents an osmotic pressure. You're literally squeezing the charge in together. And it's the osmotic pressure of these counterions that really predominates in the interaction, and which leads to this negative interaction, this repulsive interaction between the particles. And so you can write the equations for this. It works out that this is a screened Coulomb interaction. That's shown here. So the Coulomb interaction gives you a 1 over R term. It's screened. The screening length is given by the Debye length. It depends here. It's shown here. It depends on the square root of the concentration of ions and on thermal energy. And so that gives you a repulsive interaction that arises really from trying to squeeze together these ions. And often that's called the disjoining pressure because you're trying to get these two surfaces close together. So you might think that it's really the repulsion between the positive surfaces, and you can think of it that way. But really, the best way of understanding it is that you're trying to squeeze, you're putting an osmotic pressure and squeezing the ions together in a way that you can't do it. Of course, what this assumes is that the number of ions in between the surfaces are just always negative and due just to the counterions. This changes if you have, for example, two surfaces of different charges. Here I'm showing two surfaces of different charges. You still have the counterions in the middle, but now you have these different charges. And in this case, you're trying to compress the counterions. They do exert an osmotic pressure, but it's not really symmetric with the osmotic pressure of the case of the two negative surfaces, because now you have positive and negative charges. The counterions are both positive and negative, and they can combine with one another to essentially neutralize one another. These two can neutralize one another, and so these two now are no longer interacting with the ions on the surface. There's enough Coulombic interaction just for them to interact with each other. And so they're no longer bound in this region between the two surfaces, and they can diffuse away. So they're no longer trapped in between them. And that means that the ions that lead to this disjoining pressure are screened and no longer no longer trapped there, and so the disjoining pressure decreases, and as a result, the stabilizing effect of the negative interaction is lost. And so they escape, and the particle and the surfaces come together and can stick together. So very generally, if you have, for example, this stabilizing pressure due to this disjoining pressure, this charge, this screen Coulomb interaction, very generally you're going to have an interaction energy, a two-particle interaction energy for two colloidal particles that looks like the diagram shown here. There's a repulsive, there's an energy of interaction as a function of separation. If I imagine that, say, somewhere here might be the 2 times the radius or the diameter, then I'm not drawing the fact that there's a very sharp, essentially infinitely steep repulsive interaction drawn right here that prevents the particles from overlapping. But in addition to that, there's an attractive interaction due to the van der Waals effects that's shown by this component, and there's a repulsive interaction that's shown here, and the sum of these two leads to a well, an attractive well here, with a repulsive barrier given by this part, and an attractive interaction here. So this repulsive barrier, if the height of the repulsive barrier, shown by E barrier, EB, if that's much greater than KT, then the colloidal particles can never come close enough that they become attractive to one another, and then they become stable. But notice that this stability is really a kinetic effect. It just depends on the height of the barrier compared to KT. So the particles can be stable for very long periods of time, just depending on the height of the barrier. You absolutely need to have this repulsive barrier in order to retain the colloidal stability. You need to have it due to some example. Now, here is a movie that doesn't play, but shows images of colloidal particles. In the movie, these colloidal particles would be undergoing Brownian diffusion, but notice that the particles are really, on average, separated by the same amount. That means that they're feeling the repulsion of their neighbors, and they're packed close enough together that their separation is actually less than the typical distance of the repulsion. So there's always some repulsive interaction, and the particles are in a system where they're constantly repelling themselves from all the neighbors, and as a result you don't see the particles approach close to one another because of this repulsive interaction, and you see them adopt this structure where they're more or less separated on average by some distance. You can actually measure the nature of the repulsive interaction by just recognizing that if you plot the separation between the particles, that's set on average by the thermal energy, because it's just distributed by the thermal energy. And so you can write the interaction as just the logarithmic distribution of the particle separations, and that's related to KT as shown here. And so here's just some data that show the repulsive interaction that is due in this case, and this is obscured a bit, but this is 1 times the radius, and this is a relatively short range interaction, but not that short ranged. If, for example, you take the same system and, okay, there's a question here. Does this repulsive interaction depend on the colloid being in an aqueous medium? Not necessarily, I've considered an aqueous medium in this case, but I will show you examples of what happens in non-aqueous medium. All it depends on is that there is an interaction of the sort that I've showed you, that there is some repulsion between the particles, and the fact that you can see this average separation means that the range of the repulsion has to be greater than the separation of the particles. So there has to be some relatively long-range repulsive interactions. As long as you can achieve that, it doesn't matter what the medium is. It's easy to do it in an aqueous medium because then you can use charge, which gives you a relatively long-range interaction. In actual fact, charge can also surprisingly play an important role for interaction between particles in non-aqueous medium, for example in oil, but in that case the dielectric constant is much less, and so the range of the interactions are, if anything, much longer. So you can still see charge effects in oil, but they're actually much easier to see because the typical range of the interactions becomes a factor of about 10 larger than what you see in aqueous medium. Okay, to just go back to these slides, here on the left is a repulsive interaction with the particles well separated from each other. If you add salt to screen out the repulsion, so if you go back to the case where you have those, say, those negative ions in solution, if I add a lot of positive negative, I add salt to increase the charges in solution, that has the effect of screening out the charges so that there's so many charges that you don't see the effect of the positive surfaces maintaining neutrality. I mean, of course, neutrality has to maintain, but there's so many more charges that the actual interaction is decreased, and so the range of the repulsion is much less. And so here you see that the particles are much more randomly distributed. So this is just reflecting the fact that the interaction now is much shorter ranged and is less, the range of the interaction is less than the average separation of the particles. So they no longer adapt this sort of typical separation behavior. So here is again just plotting the interactions, and you can see it's a little bit subtle, but if you look carefully at these two interactions, you can see, let me use the pointer, you can see that in the absence of salt, it's a somewhat longer range right down here compared to in the presence of salt, where there's a much sharper interaction. And that just reflects the nature of the interaction that's shown in those images. And what happens if you don't have charge? If you don't have charge, you have to find some other means of having a repulsive interaction. The most common is to put a polymer brush on the surface of the particles. That is, you coat the particles with a thin layer of polymer. This is relatively non-dense polymer, and you have two particles each coated with this polymer brush. As they come together, the brushes start to overlap, and basically they have essentially the same behavior, and the polymers don't want to overlap. In order for them to overlap, they have to entwine, they have to intertangle, and they don't want to do this. And the fact that they don't want to do this leads to a repulsive interaction. This is called a steric interaction. It's essentially an osmotic effect. You just can't push the polymers and make the concentration, increase the concentration, because the polymers are spreading to be as widespread as they can. As a result, you get a repulsive interaction. That tends to be somewhat shorter range, although it depends on the range of on the length of the polymers, on the length of the brush. But typically, say for micron-sized particles, the size of a brush might be a few angstrom, a few nanometers, and so it may be between 1/10 and 1% of the radius of the particle, and that begins to look very much like a hard sphere interaction, but the stabilization comes from the presence of this polymer brush on the surface of the particles, assuming there's no charge in this case. So in order to have a colloidal suspension, by definition, the colloids must remain stable. They must remain suspended. And you work very, very hard to, in studying colloids and creating and synthesizing colloids, you work very hard to create suspensions that have this repulsive interaction enable you to retain the stability of the particles. However, what happens very often is that the stabilizing interaction disappears, and if that happens, then the particles no longer remain stable. The suspension no longer remains stable, and you destabilize the colloids. Because this happens quite often technologically, it's actually important for us to understand something about the nature of this destabilization. And in fact, the structures that you get are themselves quite interesting and are worth trying to understand a bit. So let's try to understand something about what happens if particles are destabilized. So to destabilize particles, this is a diagram. This is actually taken from an old colloid book. To destabilize particles, this is the original stabilizing interaction. If you add salt or decrease the charge on the particles, then you go from this long-range interaction. The range of the interaction gets shorter. You get an interaction that might look like this, solid line. The height of the repulsive barrier now becomes much weaker. You can actually also get into this secondary minimum shown here. This is the primary minimum. Sometimes you get into the secondary minimum where the particles become weakly attractive, but more typically you destabilize them completely so that the interactions are just dominated by the shorter range van der Waals interaction, and you're left only with an attractive interaction. And we can understand what happens when you change the nature of the interaction from this strongly repulsive interaction to this this attractive interaction. Then you end up where the particles begin to stick together. And here are some images of that were taken for gold particles that have been allowed. The interaction has been changed from repulsive to attractive, and they've been allowed to form these larger scale structures. And let's try to understand something about the nature of these structures. These are very typical structures that are seen when colloidal particles become destabilized and begin to aggregate or stick together. So first of all, we should understand how rapidly the particles stick together. There's two possibilities. In one case, if the interaction is decreased so that there's still some repulsive barrier, as shown here, then each interaction, each collision between two diffusing particles, if they come close enough together so that they collide, in most cases, this barrier could be enough to prevent them from actually sticking. However, if they collide with one another enough times, they will eventually overcome this barrier and fall into this attractive minimum. So this is where you get partial stabilization. It takes many collisions for the stability, for the particles to become unstable. On the other hand, if you completely lose this repulsive barrier, as shown here, there's no repulsive barrier at all in this case, then every collision will lead to the particles to stick. And Ben is asking a question: what is the time scale of this partial stabilization. So there's two timescales you might ask, and that is, what timescale does the destabilization occur? That is, how do you go from the stable case to the unstable case? And that can be done a variety of ways. For example, if you add salt to the solution to salt out the colloids, it's just the mixing time of the salt, which can be milliseconds, or other ways of changing the stability. It's typically milliseconds, and then you have a sample that starts that was originally stable, then becomes essentially instantaneously unstable. Then you might ask, well, how long does it take to actually cause the formation of the aggregates? And that's something I'm going to discuss in a minute, because that depends on how long it takes for the particles to find one another. And that's the topic of the next little discussion. The main point is here, I have a destabilizing interaction that there can be some remnant stability, but it may not be enough to keep them kinetically stable indefinitely. In fact, you can write what the stability constant is. It's just, what is this U maximum, and I'll go back and show that here, that this, in this case, is this value. This is the stability factor. You compare this to KT, and the ratio of this to KT is the stabilizing factor. Then it's just the collision, the attempt frequency, times this stabilizing factor, and this, the exponential of this compared to KT is called the stability factor. That's shown here. And everything is slowed down by this destabilizing factor. So that tells you what the effect of the partial stability is. Now, let's address the time scale of the interaction and what happens. And so let's just try to understand something about the nature of the behavior. If you have stable particles, you have all these particles here, you have some volume fraction phi, you have some radius of the particles, and they're diffusing around. The diffusion coefficient is given by the Stokes-Einstein equation. So these particles are diffusing around, and occasionally they hit one another, or they come close enough to one another that the repulsive interaction that provides the kinetic stability is preventing them from sticking. So that's shown here. They might diffuse around, this particle might diffuse around, and then the question is, what happens at this point? If they're stable, they bounce, they don't stick to one another, and they just continue on their paths, and they diffuse away. If they're unstable, then there's some probability that these particles will actually stick to one another, and that's given by this destabilization factor. If there is no repulsive barrier, then they'll stick immediately when they come close together, and the system will destabilize. And then it just depends on the rate of destabilization, how fast they destabilize, just depends on the likelihood that these two particles collide, and that's really a problem in diffusion, not a problem in colloid stability. Now you might ask, how long does that take? And here's a diagram which suggests one way of calculating it. If you have two particles that are separated, say on average by the distance between two particles, you can calculate that. That's sort of like the cube root, or 1 over the cube root of the concentration. If you have a certain number of particles per unit volume, if I take the cube root of that volume of the particles, that gives me the average separation between the particles. And the natural way of calculating the time scale, because it's a diffusive process, might be to calculate the diffusion time. That is, the square of this distance divided by the diffusion coefficient of the particles. And since this distance is related to the cube root of the concentration, you would get something that scales as 1 over the concentration to the 2/3. If you do that calculation, you will actually get the wrong result. And the reason is really fairly simple. And that is, although I'm showing here this diffusive path for the particle to diffuse here, in this time frame, all you've done is calculated how long it's taken for this particle to, on average, diffuse a distance s. It could be in any direction, anywhere along here. So it's very unlikely that it will actually have hit this particle. It can diffuse in any other direction. So if that's the case, then you have to really redo the calculation. And the right way of thinking about it is to imagine that this particle has to somehow collide with this particle, but the way, in order for it to do that, it doesn't want to just diffuse this distance, but rather it wants to explore the full volume occupied between two particles. If it explores the full volume, then it's certain to collide with another particle in that volume. And you can write that volume as the radius squared, that's the area, the cross-sectional area of the particle, times the contour length of its path. And the contour length is just the number of steps times the step length. The number of steps, since it's a diffusive process, is just this radius squared divided by, I'll just take as the step size, the particle size. So it's it's the radius divided by the particle size squared, times the step length, which I'll just take as the particle size. So this gives me the contour length is just this radius here squared divided by the particle size. The particle size is just what I'm taking as the step size. You can redo this calculation with any step size you want. So now if we say this is the volume that you want to explore, this is the volume of the path, this is the volume, so the time, this is the volume, where did I get that? This is the volume here, this is the contour length times the radius squared, so I take the product of these things, that's the volume of the path, is r squared times the particle size, and the time that it takes to diffuse this distance, again, is just the contour length squared divided by the diffusion coefficient. And so the volume per time, or the total, the volume per time is just the diffusion coefficient times the particle size. The volume required is 1 over the concentration. And so if you use this and calculate the time, you get this expression here, 1 over the concentration times, not using the pointer, 1 over the concentration times the particle size times the radius. And this has a completely different scaling. And this is really the time it takes for two particles to collide. Again, the calculation is done by calculating how long it takes for a particle to explore the full volume between that exists between that on average that one particle occupies, or the average volume per particle. And once it explores that full volume, then it certainly will collide with a second particle. And notice that you get a very different scaling. You will get the same result if you calculate the flux of diffusing particles onto a sphere of radius a, and that's how this was originally calculated. But I thought I would just go through the physics of understanding this. So the rate, 1 over this time, is given by the concentration times the radius times the diffusion coefficient. Notice, interestingly enough, that if you're looking at particles of the same size, the diffusion coefficient depends inversely on the particle size, and this quantity depends on the particle size. So the actual particle size cancels out. So it really just depends on some fundamental quantities, kT and the viscosity, as well as the concentration of the particles. And this is called the doubling time of this. It was first calculated by Smolkovsky. So now let's look a little bit at the structure of the particles. Let's see, I'm going to continue on for a few minutes to describe this, so I'll go for another 15 minutes or so. If you look at the structure of the particles, images of different structures that form. So the way these images are taken is to allow this destabilization. Let me go back and show you this destabilization, what I mean. Imagine this diagram here, and we start with these stable particles. We allow particles to collide. whenever they collide, they stick together and they form larger and larger structures. And these are images of structures taken. These are electron micrographs of colloidal aggregates that are taken of different sizes. You can see this. These are all, the scale bars are shown here. This is 500 nanometers. This is 50 nanometers. The particle sizes are the same. These are just aggregates of different sizes that are shown under different magnifications. And the interesting thing about this is, notice that in all cases, these are images taken with an electron microscope of three-dimensional particles, but you're seeing, of course, only a two-dimensional image. You're seeing essentially a shadow graph of the particles. So you can think of the aggregate being collapsed down onto the surface. Notice in all cases that you can see through them. That is, there are holes in all cases that are sort of comparable in scale to the structure itself. Here's a hole through the object here. Here's a hole through the object here. These holes get larger and larger as the aggregates get larger. Here's a hole here. Here's a hole here. All of the holes in the structure are as large as the structures themselves. So this is a rather unique structure. These look very disordered, but in fact you can make some sense of them by calculating. If I go back to here, if I calculate what the mass of these particular aggregates are, I can do that just by counting the number of particles that make up the number of primary particles that make up the aggregate, and calculating the size. I can calculate, for example, the radius or the radius of gyration of these structures, and I plot the mass as a function of the size on a log-log plot. Here's the log of the mass plotted as a function of the log of the size. You get a perfect straight line, a perfect log-log correlation. And if you get a straight line on a double log plot, that means you have a power law. And the slope of this gives you the exponent of the power law. And so in this case, you have that the mass scales as the size to some dimension. This dimension, if I go back here, is 1.7. Remember, this is 3 dimensions. So if it were a solid object, this should scale, the mass should scale as the radius of the object cubed. In this case, it's scaling as the radius of the object, but it's scaling not as the cube, but as some lower power. This is called a fractal dimension, and the fractal dimension is less than the dimension of space. What that means is that it's increasing, the mass is increasing, but it's not increasing as rapidly as space as the dimension of space is. And so an object that looks like this, first of all, has no characteristic length scale. So it's scale invariant because it's scaling as a power law, but it does exhibit this scale invariant structure. It does exhibit this particular self-similarity. And this, an object like this is called a fractal. One of the important important characteristics of a fractal object is that if you calculate its density, that is the mass divided by the volume, the mass scales as the length, the length scale to the fractal dimension, whereas the volume scales as the length scale to the Euclidean dimension. And since the fractal dimension is less than the Euclidean dimension, this number, the fractal dimension minus the Euclidean dimension, is less than 1. It's negative, and so the density actually decreases with size. And you actually know that. If I go back and I show you the shape, you know that that must be the case, because as you get larger and larger, you have more holes. There's more empty space, because the holes basically occupy the same volume, or the same the holes are always the same size as the object itself. So there has to be more and more holes. So it's actually getting less and less dense. And that's the nature of any fractal object, that is, density decreases with size. You can see this in a different way. Instead of looking at how the mass grows with size, you can ask what is the correlation, the two-particle correlation between two particles. What's the correlation between two particles within a structure? And that just depends very much like the way the density depends. So in 3 dimensions, it's the 1 over the spatial separation between two particles to the Euclidean dimension minus the fractal dimension. And in 2 dimensions, it's the same thing where the same fractal dimension is. So actually why I'm showing this is that if I were to look at a 3-dimensional object, so I can take one of those clusters and do this in 3 dimensions, I would expect the correlations between the object to go as 1 minus 3 minus the fractal dimension. But if I collapse it down into 2 dimensions, and I just look at what happened to the 2-dimensional projection, I will still see something that decays and falls off. So the correlation decreases as you go to larger distances if the fractal dimension now is less than not 3 but less than 2. So this is actually a nice way of telling the difference between an object that has a fractal dimension of 2 or 3. It's whether the correlations, you can see correlations that fall off in the projected image. And so if I go back and look, let me show you this image here. If I look at this image and I calculate the correlation function, that is, I calculate the particle-particle correlation function between all pairs of particles, I end up with data that looks like this. And you can see that again, plotting it on a log-log scale, there is a decrease in the correlation function, a logarithmic decrease in the correlation function. In this case, the slope of this decrease is 0.25, so it's negative 0.25, and that corresponds, because it's a 2-dimensional projection of a 3-dimensional object, that corresponds to the difference between 2 and this, which corresponds to a fractal dimension of 1.75, which is quite consistent with the value that you measure by looking at the correlations between the masses of different objects, which was 1.7. Here in this case it's 1.75. So these objects really are these fractal or scale invariant objects. And that comes about because of the way the particles are colliding and coming together. So if I go back and I look at the aggregation process, I'm showing you now here 2 different aggregates. This is the one I've been describing. This is formed by reducing the barrier so there's absolutely no repulsive barrier. If you leave a repulsive barrier, you get this object shown here. Notice here you can, in many cases, not really see through this object. Here, of course, there's a hole, but here it's much more dense. And since this is a projection, you can immediately say, well, because it's essentially as dense as space, the fractal dimension is going to be something between 2 and 3. It's going to be greater than 2 because I'm looking at a projection and I can no longer see through it. There's a very distinct difference between these two. And just by looking at this, you can get some sense of what the fractal dimension is. In fact, analysis of these objects will show that its fractal dimension is something around 2.1. So how can we understand this? Well, remember I showed you that what was happening was it comes about because the particles collide to one another and start to stick. As they start to stick, they form clusters, and the clusters themselves then begin to diffuse, and the clusters collide. So you get aggregation not just of particles, but aggregation of clusters. And the clusters are themselves undergoing diffusive motion. That's shown here. Now, if you have these fairly tenuous clusters, and they're undergoing diffusive motion, it's very, very unlikely that this end of this cluster can go all the way in and stick here, because it's very likely that through the diffusive motion it will stick on the outside. And so you'll end up with much, much more tenuous structures. That is assuming that the particles stick immediately. If, on the other hand, they don't stick immediately, they continue to diffuse, then the particles can enter into these regions and you can get a much more dense structure. You can sort of understand that by understanding a bit of the behavior of this. You have the Euclidean dimension, that's the dimension of space. So we're talking about 3 dimensions, typically. If you were looking on a surface, it would be two dimensions. You have the fractal dimension, that's a dimension, the fractal dimension is telling you how tenuous the clusters are themselves. And you have the dimension of the motion. So if you have a random walk, if you have diffusive motion, that's like the particles or the clusters undergoing motion that itself is a fractal and has a fractal dimension of 2. That's the way you describe a random walk. It's motion that has a fractal dimension of 2. If, on the other hand, they were sort of being shot from a gun and they were going straight through, there would be ballistic motion. That would have a trajectory motion of 1. Another way of understanding this is if they actually don't stick. So the likelihood of sticking is very, very low. In that case, the limitation of sticking is no longer the fact that they stick whenever they collide, but rather they take a long time to stick. And so in that case, the dimension, the fact that they're undergoing diffusive motion, and if I go back here, the fact that this particle, for example, will be diffusing and therefore will always stick on the outside is relaxed, and this particle can stick anywhere with equal probability. That's like saying it has a trajectory dimension of 0. It doesn't care about the trajectory. It will stick wherever, on average, anywhere. And so that has a trajectory of 0. And then you can just ask, what's the nature of the cluster? How tenuous is the cluster? In some sense, it depends on the sum of all these dimensions. It depends on the fractal dimension of the 2 objects, that tells you how tenuous they are, and the dimension of the trajectory. So imagine if I have a single particle, that's shown here, for example. If I have a single particle, its fractal dimension is 0. So it has a fractal dimension of 0, and it interacts with the cluster that, say, that's formed by these cluster aggregation pictures. That has a fractal dimension of 1.75. But the fact that the trajectory, that there's diffusive motion, the trajectory dimension is now 2. The sum of all these dimensions is greater than the dimension of space, and that says that these particles can't really interpenetrate. The same thing occurs even with more effects if you have 2 fractals that are undergoing Brownian motion. Then the total dimension is much greater than 3. But notice if you had a single particle, a fractal object, and something that was reaction limited, that is, where there was equal probability of sticking anywhere, then the trajectory dimension would be 0. And so the sum of all these dimensions is actually less than 3. If it's less than 3, then you don't have the particles sticking on the outside. You have them able to penetrate. And the fact that they can penetrate actually means that the object is going to get much more dense. And that's essentially what you were seeing when you saw those clusters that were formed by particles that were not destabilized completely. They were able to interpenetrate much more and have much more dense structures. Let's see. I think that at this point I've gone on for an hour and a half. Maybe I will just stop here and we'll pick this up in the next